Right, we're looking here at the 2009 Queensland Senior External Exam Physics paper from 2009, paper 2. We're looking at question 8. First thing we do is we carefully read the question. An experiment was performed using standing sound wave patterns to determine the speed of sound. Two speakers connected to a frequency generator were placed several meters apart facing each other. 4 different frequencies were produced and the distance between nodal points was recorded each time. So the results were for frequencies of 250, 500, 1000 and 2000, the distance between the nodes in centimetres, 66.7, 33.3, 16 and 18.3. On the graph paper provided on page 1 of your response book, use a graphical method with this recorded data to find the speed of sound. Let's go through and let's importantly identify the important information. We're actually talking about a standing wave pattern. 2 loudspeakers are connected several meters apart, so they're facing each other. 4 different frequencies of sound are produced, so we've got frequencies 1, 2, 3, 4, like so, and the distances between nodal points. So nodal points 1, 2, 3, 4, like so were recorded. There's the results table. First thing we need to do is we need to draw a diagram. Now I'm going to draw a diagram just to represent what happens when you have 2 speakers facing one another. And let's imagine that the speakers here are 3 wavelengths apart. So there's speaker 1, here's speaker 2, and we draw wavelength, we draw wavelength, and we draw wavelength like so. So there's our interference pattern. For a standing wave, we're actually interested in the pattern that sets up directly between the 2 speakers. And I can go through and I can mark out wherever I get a crest and a crest meeting, like so, you'll have a maximum. And also where we have a trough and a trough meeting, we'll have a maximum. So here, there would be a double trough, a trough from this particular wave, and a trough from this particular wave, and here we have a crest from each particular wave. And so therefore that will be a maximum, 2 troughs, 2 crests, 2 troughs, 2 crests, 2 troughs, 2 crests. Now that may look a little bit crowded, but halfway between those we will have nodes. So node, 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 node. I think you can see here from this particular diagram that the nodes separation is half a wavelength. And so that's the important thing to realise. With a standing wave, the maximum are half a wavelength apart and the minima are half a wavelength apart. So where in our table here we have distances between nodes, I'm starting to come right down here where I'm doing a bit of evaluation. From my understanding, I know that the wavelength is actually going to be twice this distance. So 66.7 divided by 2, calculator, 66.7 times 2 equals 133.4. Now that'll be centimetres. Double 33.3, 66.6 centimetres. 16 will be 32.0 centimetres, and 8.3 will be 16.6 centimetres. So I'm able to go through here and do the calculation to actually work out what the wavelengths are. Now pressing on that, I've just gone about and calculated my distances. That should be on my vertical axis, and so I'm going to draw the vertical axis here, and I'm going to call that lambda, and I'll start off at 0. And I've got to be able to go up to 133. So if I go up here in 25, 50, 75, 100, 125. So if I go up here 25 centimetres, 50, 75, 100, 125, I make that in centimetres. Now, I don't actually want to, make it in centimetres, I want to make it in metres. So if I go multiply by 10 to the negative 2, that will actually take it into metres for me. Okay, so that's my wavelength. So on my horizontal here, because I want to be able to calculate a velocity, and it's always a distance versus a time, I want to change my frequencies here into periods, and that'll be in the unit of seconds, so that I'm therefore then able to do a distance versus time graph. And when I do my distance versus time graph, the gradient of that, of course, will be the velocity, and so that's where I'm after the speed. So let's do the reciprocal of these particular numbers. So we're starting off with 250, do the reciprocal of 250 equals 0.004, because frequency and period are the reciprocal of one another. So let's 500, press the reciprocal button, equals 0.002. Let's do 1000, press the reciprocal button, 0.001, cancel, and let's do 2000, press the reciprocal button, equals 0.0005. Right, so therefore we go. With my horizontal axis, I want to be able to go with up to 4 thousandths of a second. So I could make this here 1, 2, 3, 4, like so, and multiply that by 10 to the negative 3, and I've got it in seconds. Now I can plot my values. 0.004. 0.004 is here, and that comes out to 133.4, like so. 0.002 here comes out at 66.6. 0.001 is here, comes out at 32, and 0.0005 comes out at 16.6. So there's my line. I draw my line of best fit, which should come through the origin if I've done it of any particular value, and I need to be able to work out the slope, which is the rise over the run. So if I were to do the rise here, the rise goes up 125 by 10 to the negative 2, and I divide that by the run, and the run here I'd make that 3.8 by 10 to the negative 3. So plugging that straight into my calculator, 125 divided by 3.8 equals 32.9, multiplied by 10 to the negative 2 minus 3 is of course 10 to the 1, so I get a value here of 329 meters per second for my speed of sound. Now finally, does this answer make sense, and do I have the correct significant figures? So 329, these ones here, 3 significant figures, 3 significant figures, 3 significant, 2 significant figures. These ones here, we'll disregard them. I want to give my answer to this particular value here, so I'll write that there as 330 meters per second. And that's in the same format, if you like, as the 250, the 500, the 1000 and the 2000. So speed of 330 meters per second, yes, I'm happy with that answer.